Okay, so we are live. Welcome everyone to our third week of Intro Physics 2. And if you've been following this series, this live stream is a weekly live stream during which we cover the important topics of the week and we summarize the things that you should really know, and then we try to apply those to physics problems to learn how to solve physics problems together. And this week we're going to be moving on to electric potential. Electric potential is a part 3 of 3 of basically electric fields or electrostatics, if you want to think of it that way. From here we start moving into circuits, and circuits are far more applied than the first 3 chapters, and we don't gain from circuits new knowledge pertaining to electric fields, right? So if you're talking about electric fields or electrostatics, then chapter 1 was electric fields, point charges, Coulomb's law, electric force, all of that stuff. Then Gauss's law, which is a nice, clever way to find the electric field of a charge distribution that has enough symmetry. And then today we're talking about electric potential. Probably, if you poll students, the worst of the 3. Students tend to not like electric potential. There's a few chapters like that in Physics 2, electric potential being one of them, the reason being that electric potential is very abstract. It's hard to conceptualize. It is not a quantity that I can draw really, because it's not a vector, it's just a number. And so it's really hard to wrap your head around it. And so we're going to try to do that. We're going to try to wrap our head around electric potential today. Now, before we start, let's just go through real quick the resources, and you probably already know this, but bear with me. If you'd like to get all these live streams packaged in a nice course that is a free course, you should go to psychedemia.com/livestreams. Enroll in the Physics 8B live stream. You will find all of these live streams. All of the problems that I do during the live stream will be in there as well, so you can attempt them before watching the solution. And there's also a lot of solved homework problems in there as extra practice if you want to get some practice. So feel free to check that out. If you need more help in physics, we have study guides with 2 options. You can self-study, and then you get access to the study guides with solved problems step by step with video solutions, old exams, things like that. And if you need more help than self-study, or you just want to get access to me for the duration of your course, you can sign up for the Masterclass option when you enroll, and then you will get basically unlimited help via Slack, mostly from me when it comes to physics. And if you sign up for the Masterclass, that comes with a guarantee that if you don't get some kind of A, we will refund you 90% of the cost of the Masterclass, because we feel pretty confident that if you work with us for the entire course, you're probably in a good position to get an A. All right. So, electric potential. I try to always think about how I teach electric potential and come up with the best way possible. I think the truth about electric potential is this. There's a lot of material, and it's very easy to get submerged by all of this material at once. And I think that it may be best to cherry pick a little bit today, and to touch on the important things that you need to have in mind when it comes to electric potential, to at least somewhat make peace with the concept and have in mind what different types of questions you might be asked. For the most part, we're going to try to get good at finding the electric potential created by a charge. And there's different ways to do that, and there's different consequences that come from being able to do that. So, let's just start with a definition. It seems like a definition is like the good place to start anyway. So let's go through this. Electric potential is a property of the space surrounding charge. By the way, that's like the electric field. Okay, if you have a charge, doesn't really matter the shape, in the space surrounding it, you have a property that's called electric field. You also have a property that's called electric potential. Electric potential is denoted by V. It's a number, and it represents the available electric potential energy per unit charge at a point. Okay, so we need to unpack that. Specifically the per unit charge part, because that's the part that makes it a little strange perhaps. But it is very interesting to have a quantity per unit charge. You might wonder why that is, but actually let's talk about why that is. Let's say you want to go to, you go to the store and you want to buy limes, just making something up. And limes are 30 cents for a lime. I don't even know if that's realistic, but it doesn't matter. The price is given per lime. Right? You just need to then buy as many as you need, and if you need 10 limes, then you pay $3 because each one is 30 cents. But it's a lot easier to have a quantity, a price per quantity, than just a price. Okay? Well, first of all, if it's a price per pound, then you have to go weigh it. It's still a price per something. It's just a little more complicated. But what you wouldn't want is someone to say, oh, limes are $10, but you have to buy, I don't know, 50 limes or whatever it is. I'm like, okay, well, that's not very helpful. I need 2. Like, how much do I pay for that? So the idea of having a price per quantity is not necessarily a bad idea. It actually is something that kind of makes sense in everyday life. Well, if you want to think of energy in the same way, well, perhaps we can just have energy per charge like that. Just tell me how much charge you have. I will tell how much potential energy you have. So let's try to draw a parallel. We'll draw a parallel with mechanics because that's something that it's meant to represent or meant to be analogous to. So in mechanics, let's say this is the ground. Here's a mass M. A mass M is somehow at a height h above the ground. And we know that we're free to choose our reference for gravitational potential energy anywhere we want. Typically the ground, the reason being that it's pretty natural for us to measure height from the ground up. So I tend to put my reference for potential energy on the ground or at the lowest point in the problem. So if that's the case, then we know that the gravitational potential energy of this mass is mgh. Okay? That should not be new information. The higher h, the more potential energy you have. And this is a property of the space surrounding Earth, right? In fact, the position of the mass in the Earth's gravitational field dictates its potential energy. That's what potential energy is. It is energy due to your position, right? So, if that's the case, and we agree on that, let's do the following. Let's find energy per mass. Just divide by m. That would be GH. Now GH, of course, is independent of mass. That's the whole point. The same idea as having a price per line. Well, we would want energy per mass in mechanics because all of Physics 1, for the most part, mechanics anyway, is the story of mass. Physics 2, that's really the story of light, but at the beginning of Physics 2, it tends to look like the story of charge. Charge is what we care about. And so the question then is, could we define a quantity here that would represent electric potential energy per unit charge, and from that quantity I might be able to get electric potential energy. Okay, so this is, you could call this potential. We don't usually ever introduce just GH in mechanics. We don't need to. We just use MGH and it works fine. But this is the available gravitational potential energy per kilogram at a height h. So if this is 100 joules per kilogram and you put a 5 kilogram mass here, you have 500 joules of potential energy. Okay? So we could have introduced this in mechanics, we just didn't. So let's now translate this to a problem that deals with charge and electric fields in Physics 2. Okay, so let's take this charge Q. This charge Q is going to be fixed. It's not going to move. And at some distance r, from Q, there's going to be a quantity, V, which is called electric potential. And our goal is to figure out what it is. Now, electric potential will be related to electric potential energy. And by definition, potential energy is energy due to position. In this case, due to your position within the electric field surrounding the charge. So, let's try to make the parallel here. V, I'm going to write question mark. V equals question mark because the goal of this chapter is to figure out what V is and how we compute V, which we'll get to. But this will be the available electric potential energy per coulomb, so per unit charge, at a distance r from Q. Okay, I don't know what it is yet, and we're going to try to evaluate it, but if I am able to find V, then I can get U sub E. Now, E because of electric fields, it's electric potential energy. Well, if V is potential energy per charge, well, how much charge do you have, let's say Q, multiplied by V, will give me electric potential energy. And we're going to be very interested in electric potential energy, and we'll see why. So really, the goal on a practical level is kind of to get to this, right? To get to the electric potential energy component. But to do that, we need to figure out what V is first. So we're going to talk about the different ways that you can compute V based on what you have. You could have a point charge, multiple point charges. You could have a continuous distribution of charge. Perhaps you don't have any of those, you just have an electric field, but there is a relationship between electric field and electric potential, which seems to make sense because both are properties of the space that surrounds charge. And so they come from the same source. Seems reasonable to expect that there is some relationship between them. So we'll talk about that. Now, once again, the goal is to find V. Okay? So, let's do the following. Let's try to structure our approach the same way we structured our first lesson. The first lesson we had, or we did, we talked about electric fields, and we started with the point charge and the electric field created by a point charge. We said it's the only one for which you have a formula for the electric field that you can use off the shelf. You don't have to prove it. That's the formula. Then we said, oh, well, you know, not everything in life is a point charge, so maybe we have to talk about slice and dice. So we'll talk about that. And then we're going to stress the relationship between the electric field and the difference, in fact, in electric potential. So, how to compute capital V, or, depending on the case, delta V. Now it turns out that, I know I said we're trying to find V, which is true. What truly matters, though, is delta V. It's the change in potential, because that's going to tie to the change in potential energy. And having a potential energy of 100 and spending 50 to bring it down to 50 is the same thing as having potential energy of 1,000, spending 50 and bringing it down to 950. It's not 150 or 1,000 and 950 that matters, it's the change of 50 in both cases, which is what matters. So ultimate goal is to get delta V. But if you can compute V, then you could always just subtract two values and get delta V. So the goal here is to go over the different methods that we have to compute V or delta V. Let's start with the case of a point charge. Okay, this might be the most important case because it's the only formula that you have that you're allowed to use directly. Okay, so let's say we have a charge Q. This is some location here. I'll call it point P. A distance r from Q. Then the electric potential, capital V, at point P created by Q is given by KQ over R. That is joules per coulomb, but we use volts. Now, unfortunately, volts, well, starts with a V, just like the letter we chose for electric potential. So I try to make my uppercase V a little different when I'm talking about the quantity versus the unit. The unit doesn't have the flat tops there, but it is what it is. A V that denotes both the unit and the quantity. Not great, but sometimes that happens. Okay, so this is the electric potential created by a point charge. Note that I do not need to have anything at point P. I don't need another charge to be there. V exists purely because Q is there. That's it. It's a property that surrounds Q. If I then come and place a point charge here, well, that's a different story. We'll get electric potential energy. That, in fact, will be shared by both point charges, but the point is it'll be Q times V. So we'll talk about that in the first problem. We'll see how you can translate that to electric potential energy. But if the goal is to compute V, the easiest case is the case of the point charge. You can use this formula off the shelf. You don't have to prove anything. It's a given. Okay? Now, of course, we should probably, while we're at it, talk about the case of multiple point charges. Okay, so what happens if you have Q1, Q2, I'll just draw 3 because that's plenty, but you get the idea, right? Okay. Well then, V, let's call it point P again. That's a good way to denote this point. This is point P. Right. Again, point P is a location. There's nothing at that point. It's just a location in space. Is going to be, by superposition, it is the sum V1 plus V2 plus V3. Okay. And of course, it continues if you have more than 3-point charges. Okay, you probably write it like this. You would say, oh, well, V P is going to be the sum over I of all the different VIs. And I can be going from 1 to however many you want. The point is, if you have more than 1 point charge, you take one at a time. You find V for each one. You add them all together, and you get V at point P. And because V is a number, it's actually very easy to add them all together. It's not like a vector where I have to worry about components. I just add the values together. Okay. So then we have the case of a continuous charge distribution. All right, so here's where stuff gets interesting, because when we draw this in physics, we need to draw something, but the something is not going to be very helpful because it's going to be very abstract. It's meant to represent any possible scenario. So I'm going to draw a blob of charge, but it could be just a wire. that's bent a certain way. It could just be a surface, it could be a volume, it could be all of those things. Right? And what we're going to say is that if we're able to identify a little piece of charge dq, then we will get the electric field at point P, or excuse me, the electric potential at point P, by integrating k dq over r. Now you might have to integrate just over one dimension if it's, let's say it's a line of charge. Maybe you have to integrate over a surface if you have a disk of charge. Maybe you have to integrate over a volume. Depends, right? But this is known as slice and dice. Now we'll do a case of slice and dice at the very end of today's session. But I want to present it this way because this is the same order that we went through electric fields in the first chapter. Right? We're starting with a point charge, saying, okay, if we have multiple point charges, superposition. If you have a continuous charge distribution, well, it is actually still superposition. It's just that you have an infinite sum, which is really an integral, over the entire charged object. Okay, so those are methods that will allow us to compute V, which is the goal, but from scratch. And you will get V at some point P. Fair enough. If you know V at any point, you can always compute delta V, right? You could find V1 at point 1, V2 at point 2, and then compute V2 minus V1. You know the individual quantities anyway. However, there's a fourth way, okay, which is deriving delta V from E. Okay. Now I'm going to do a bit of a sidebar here before I give you the formula. But there is a way to derive delta V from E. And of course that doesn't give you V, it gives you delta V. You just get the change directly. You don't know what V1 and V2 are, you just know V2 minus V1, let's say. But that's okay, the change is typically what matters anyway. So let's take an electric field. Right? I'll take an electric field line from here to here. And we said in the first chapter that electric fields point from either plus to minus, or from plus they go all the way to infinity, or they come all the way from infinity on to minus. Those are our three options, which is fine. We didn't have a better way of describing it in the first place, but now we have a better description possible because we've introduced electric potential. And a property of electric fields is actually to point from high potential to low potential. So a better way of describing an electric field in terms of direction is to say that E points from high potential V to low potential V. Okay, so a difference in electric potential, if you have 2 points that have a different value of V, you can be certain that between them there's an electric field. And the electric field will point from high to low. Now let's assume here that we have V1 is 5 volts. Let's just assume. Okay, somebody gave me 5 volts. There's a machine created this electric field, and it comes with the information that V1 is 5 volts, and V2 at this point here. Let's say V2 is minus 2 volts. Okay, now E points from high V to low V, that's true. Okay. And let's say that now, at this location, we place a test charge Q. And the test charge Q is going to have an initial speed of 0. It starts at rest. You just put it there. And it's going to move. Let's say it's positive. Right? If it's positive, the electric force is going to pull it in the direction of the electric field. It's going to move to the right. And when it makes it to this point here, in fact, it's going to have a certain speed V final. And it will have done is spend potential energy to gain kinetic energy. Okay. So, with that said, let's just give me a second here. There we go. With that said, let's do a quick calculation. Let's say Q is 10 to the minus 6 Coulomb. Okay, well then U1, the electric potential energy, initially, here, is going to be Q times V1. So that's 5 times 10 to negative 6. So that's 5 microjoules. Okay. U2, the electric potential energy here, is going to be Q V2. That's going to be minus 2 microjoules. Okay. Now, something that we have to basically address right away is the fact that here, delta U, the amount spent, is minus 2 minus 5 is equal to minus 7 microjoules. So it looks like, if you start out with 5 microjoules, well, it looks like you've overspent your budget. Can you even do that? Like, well, how can you spend more than you have? Now, I wouldn't get caught up with this negative issue, right? Because again, the fact that V be minus, it's relative to a reference. And a lot of the times, your reference is, if it's not set for you, you can pick an arbitrary point as your reference. It's the same idea as MGH, yeah? MGH, if this is a table and you have a certain potential energy, 0 at the table, right? 5 joules above, well, you can fall below the table, right? And you can spend more than 5 joules. You can spend 7 and end up on the floor below the table. But the negative amount, the fact that you spent 7, although you had 5 to begin with, it doesn't mean anything because it's relative to a reference that you chose anyway. So just to clear that, first of all, yes, even though you only have 5, you can end up spending more, right? And the point is, if you spend 7 joules of electric potential energy, then what you're getting is a change in kinetic energy that is going to be plus 7 microjoules. Okay. And that means that if I know that, I can evaluate V final, which we'll do later on. But the point is, I can apply conservation of energy. And the reason why is because the electric force is a conservative force, just like the weight force is a conservative force. And so, for the same reason I could apply conservation of energy in mechanics if I only had the spring force or the weight force doing work. Well, when it comes to electrostatics, I can apply conservation of mechanical energy as long as the only force driving the motion is the electric force. And here the only force doing work is the electric force. It's going to pull Q from left to right and give it a speed V final by the time it reaches the right end. And it's a conservative force, so conservation of energy applies. Okay. So, that was a bit of a sidebar to just illustrate where we're trying to go from here and stress the fact that what truly matters, again, is the change, delta U, and of course delta U is going to be Q delta V. And delta V can be computed from the electric field. So V2 minus V1, which is delta V, then be equal to minus the integral from 1 to 2 of E dot dr. Now this is a formula that notoriously students struggle with in this class. A few reasons for that. But the first one is this minus sign here, because everybody's confused about the minus sign. My recommendation to you is memorize this formula as is, write it as is on the problem that you're solving, and then go from there so that you don't forget a sign, you don't mix up the order of your bounds, and so on and so forth. Because the order here matters. If this is V2, the upper bound has to be 2. If this is, hold on, there we go. If this is V1, then the lower bound here has to be V1, it has to be 1. And then the minus here is just there. The reason it's there is because E points from high V to low V, right? So if delta V is positive, you get an increase in V. Well, that would be from right to left. Bummer, E points from left to right. So the minus is there to account for direction. Right? But this equation, this formula, is going to allow me to find delta V if I know E. It turns out that's pretty interesting for me because I just spent 2 weeks plus getting really good at finding E. I know slice and dice. I know superposition if I have multiple point charges. I even know Gauss's law if I have high symmetry. So I have a lot of tools that allow me to find E. And if I can find it, then I can find delta V. Okay? So delta V is called an electric potential difference. Now, that's a complicated word, and physicists are busy people, and they know that this is an electric potential difference. That's just a lot of words. So they tend to call it potential or potential difference. And, well, we're pretty loosey-goosey about the whole thing. Some just call it a voltage. Okay, so electric potential difference is typically also known as a voltage. It means the same thing. But if you want it to be picky, a voltage should be a difference between two values of V. Except sometimes instead of voltage, we just call it potential. So it's a little loosey-goosey in terms of the nomenclature. You'll get used to it. I'm sometimes guilty of it because I'll just say potential instead of electric potential difference. But the point is, delta V is a voltage, which is a difference in two values of V. And we're going to see that in this chapter. It's interesting to know that because we can tie it to the electric field, which points from high V to low V. And then in the next chapter, when we do circuits, well, if you have a voltage, a delta V across a circuit, that will be what drives charge, electrons principally, through the circuit, right? So the delta V is an important notion. A voltage is an important notion in physics. But for now, we just wanted to get delta V in order to get delta U. That's going to be our main focus. So we're going to learn how to apply this, right? Because this is one of these formulas in physics where once it's given to you, you still are holding an empty sack. Or you have no idea how to apply it necessarily. You don't know what dr represents. You don't know how to deal with E dot dr. Now, it's a very compact formula, which is great. If you know how to apply it, it's nice to just have the compact formula to lean on, and then you unpack it every time. But we have to learn how to unpack it, so we'll get to that. All right. So let's just take a step back, and let's think about what we covered. We tried to introduce this idea that in the space surrounding charge, there is a property called potential, or electric potential. It is the available electric potential energy per unit charge at a point. And should I be able to find V, then I am able to find the electric potential energy, which is nice because I need that for conservation of mechanical energy. The question then is, how do I find V? Well, there's a few options. I can have the case of a point charge, then I have a formula that I can just use off the shelf. If I have multiple point charges, I'll do the same thing for each point charge, that's superposition. And then for a continuous charge distribution, that's another tricky formula. This doesn't really mean anything until you've seen it applied, but you do the slice and dice method. You take a little slice of your charged object, you say, well, it behaves like a point charge. I'll tell you what the total electric potential is. The price I have to pay is I have to integrate over my object, which means either over a line, a surface, or a volume. All right, and then finally, there's a way to get delta V if you know the electric field. This ties back to everything we've learned so far. Okay, we've gotten pretty good at finding electric fields. There's a lot of tools that we can use. And should we know E, then we can find delta V. All right, let's start with something perhaps a little bit simple so that we can, go from there and make things a little harder. This is going to be a nice little review of things we've talked about before anyway, but it hopefully will give a bit more of a concrete application of electric potential and help you understand it better. So we have 2-point charges that are held in place 3 meters apart. Those are the point charges A and B. We know QA, we know QB. We want to find the magnitude and direction of the force on the charge B due to A, the electric field strength at point C. That's all stuff from the past 2 weeks. 3, okay, electric potential at point C. That's what we did today. And then we're going to add some stuff to the problem and go from there. But let's start by drawing this out. Come on, there we go. Actually, I'm just going to call this QB. This is going to be QA. The distance in between the two is R is equal to 3 meters. And we know QA and QB. We want the magnitude and direction of the force on the charge B due to A. That should be hopefully pretty straightforward. Before we do that, I'll make a copy of this for later. But we know that opposite charges attract. The force of A on B is going to point to the left, and it's going to be given by Coulomb's law. Coulomb's law will give me the magnitude of F of A on B. That is going to be K, QA, QB divided by R squared, which is 9 times 10 to the 9, multiplied by, now that's a little imprecise of me, apologies. I should put an absolute value around the charges because I want magnitude. Okay, so QA is 2 10 to negative 9 in absolute value. And then QB is 4 times 10 to negative 9 divided by 3 squared. All right, so 10 to negative 9 and 10 to 9 go away. 3 squared and 9 go away. This ends up being 2 times 4 is 8. 10 to the negative 9 Newton to the left. Okay, that's week 1. It's Coulomb's law. Nothing too difficult there. All right. Then question 2 asks us to find the electric field strength and direction at point C, which is 3 meters to the right of point B. Okay, so we have another location here, point C. That is another 3 meters over to the right. Okay, and at point C, there is no charge, not yet anyway. We just want to know the strength of the electric field. Okay. We have 2-point charges, QA and QB, creating a net electric field at point C. By superposition, I can look at A first, B second, draw the electric fields, and then carefully, because they're vectors, add them together. All right, A is a negative charge. So the electric field at point C created by QA is going to point toward QA. QB is a positive point charge, and therefore the electric field created by QB at point C is going to point away from QB, so to the right. And if we want the field strength at point C, we're just going to say that the net electric field E net at C is simply E sub B minus E sub A, which is going to be K absolute value of, well, QB is positive, so I'll just call it QB. I don't really need the absolute value. It's K QB over R squared minus K absolute value of QA over R squared. Okay, another word of caution here. If you write minus because EA points to the left, which is correct, you have therefore accounted for the fact that QA is negative, because the reason why EA points to the left is because QA is negative. So you've accounted for direction, therefore here you want the absolute value of QA. If you plug in just QA here, and you plug in minus 2 10 to the 9, you're double counting your minuses. So it has to be one or the other. Either you write plus here and you plug in minus 2 10 to the 9, or you write minus and then this is just an absolute value. I tend to prefer that approach, that's just me, but keep that in mind because if you're off by a minus sign, that's probably what happened. Okay, so this is 9 10 to the 9 times 4 10 to the negative 9 divided by 3 squared minus 9 10 to the 9 times 2 10 to the negative 9 divided by 3 squared. Now that's going to be 3 squared is 9, so that goes away, this goes away. There's going to be 4 minus 2 is 2 newtons. Somehow that seems strange to me. What did I... you know what I did? I'm being a dum-dum. Being a dum-dum. That seemed too simple. What did I do wrong? What a good question. I got the wrong distance in my denominator, right? When it comes to, I should have called this, I just wrote R, but that was very sloppy of me. This should be 2R squared. There you go. Apologies. Don't go too fast like me. Okay, 2R, or call it RA, RB, do whatever you want, but the point is this should be 9. It should be 2 times 3 squared. Let's write it like that. Okay. All right, so this is going to be 4 minus, well, it's 2 times 9 is 18, and then 6 squared is 36. Okay, so this is just really 1/2. Okay, so 3.5 Newton per Coulomb is the strength of the electric field at point C, and the fact that it's positive tells me that it's directed to the right. Okay. All right, so that's the force and direction, field strength and direction at point C. What is the electric potential at point C? Please use the convention that V equals 0 very far away from the charges. Okay, this is a great question. We need to talk about this. So here's our little arrangement of charges. I'm going to get rid of this, I don't need it. And at point C, once again, it's going to be superposition. I have 2-point charges that create electric potential everywhere in the space surrounding them, and therefore at point C, to find the net electric potential, I'm going to write VA plus VB. Okay, so V at point C by superposition is VA plus VB. Now that is going to be K QA divided by 2R plus K QB divided by R. And this time, the fact that QA is negative matters. Okay, so the fact that QA is negative is tricky when it comes to vectors, right? You either account for direction by writing minus and then you plug in magnitude or absolute value of QA, or you just plug in QA, but the minus gets tricky if there's a direction associated with it. Here there's no such thing. Electric potential is a number. Right? And so you just plug in QA as negative, makes sense. A negative charge will create a negative electric potential in the space surrounding it. A positive charge will create a positive electric potential in the space surrounding it. So this is going to be 9, 10 to the 9, times minus 2, 10 to negative 9, divided by 2 times 3, plus 9, 10 to the 9, times 4 times 10 to the negative 9, divided by 3. All right, so this 2 is going to go away. And so we're going to get 9 over 3, which is 3, minus 3 because of the minus here, don't forget that. And then plus, well, this is 3, so this is going to be 12. And so we should find 9 volts for the electric potential at point C. Right, that's just superposition, that's all it is. Right, that goes back to what we were saying before. If you have multiple point charges, you just use superposition to find the net electric potential at point C. All right. So then question 4 becomes a bit more interesting. Question 4 says, now a third point charge with QD as 3×10 to the negative 9 coulomb is brought in to point C from very far away while charges A and B are held in place. How much work does this require? Take care with signs. Okay. So let's say that here we're infinitely far. Okay. So R is going to infinity. We're so far away that QD here at first has no clue about QA and QB. It's just there, kind of hanging out. And then somebody grabs it, brings it to QC. Okay, so this comes all the way over to QC. And then now we have QD at point C. Okay. Well, in order to do that, you had to fight the repulsion from QA and QB. In fact, there's more repulsion from QB because it's closer to QD than attraction from QA because that one's a little bit further. But you had to do a certain amount of work, and that amount of work was the work required to overcome the work done by the electric force in repelling QD. Okay. It should be clear, by the way, that if you release QD, if you don't anchor it there or keep it there, if you release it, it's going to go back where it came from, right? It's closer to this charge, it's going to repel it away, and it's going to go back where it came from. So, these types of questions, they're great questions, they're very common. You have to be careful with them because when you're asked to find the work, sometimes you're asked to find the work done by the electric force. Sometimes you're asked to find the work done by the person or the operator or whatever. And so you have to be careful what you're computing. The best way to do this, to not mix things up, is to actually use the work kinetic energy theorem. It's to say delta K is equal to work net. But delta K is going to be 0 because QD starts at rest. Then you take it, then you bring it to point C, and you hold it there, so it ends at rest. So there's no kinetic energy at the beginning, there's no kinetic energy at the end. Delta K is 0. Means that the net work is 0. Well, the net work is the work done by the person plus the work done by the electric force. Okay, because as you bring QD in, you have to fight the electric force that's trying to repel it away. Therefore, the work done by the person, which is anyone's guess for that matter, because I don't know how much force the person exerted over what distance or whatever. So the work done by the person is just going to be minus the work done by the electric force. Now here we got to go back to mechanics. If I have a conservative force, the work done by the conservative force is minus delta U, minus the change in the associated potential energy. Okay, so this is going to be minus, and then the work from the electric force itself is minus delta UE. That's because Fe is a conservative force. So what it means is that to find the work done by the person, we just need to find the change in electric potential energy of QD, which means we have to compute QD times delta V. Now in this case, computing delta V is quite straightforward. That's because we already know that Vc is 9 volts. We also know that V infinity is 0. We're told to take V as 0 at infinity. By the way, there's a reason for that. Okay, the reason is that these point charges, QA and QB, create an electric potential that's pretty much kq over r in form. Well, math leaves you no choice. This goes to 0 if r goes to infinity. And so it necessarily has to be the case that V is 0 at infinity if all you are dealing with are point charges. Now that changes if you have an infinite line of charge or an infinite sheet of charge, or the types of things that we saw in Gauss's law that were not spherical charges or point charges. In that case, if you have an infinite cylinder of charge, you may not claim that V is equal to 0 at infinity. That's not true. It just happens to be true in the case of the point charge, and so that's why we have V infinity is 0 here. Okay. So work done by the person is Q times delta V. That's pretty straightforward. Delta V is going to be Vc minus V infinity. So the work done by the person is going to be QD times Vc minus V infinity, which is 0. So that's going to be QD is 3 times 10 to negative 9 times 9. That's 27 times 10 to negative 9 joules. All right. And that is the amount of work done by the person. All right. And then finally, let me just make one last copy of this to address the fifth question. Now we have QD here, by the way. The last question is, what is the total electric potential energy stored in the final configuration of all three charges? Please use the convention that P is 0 if all three charges are far from each other. Okay, that's the same convention as before. All right. Now here, things become really interesting. Because, let's just write the charges so that we have them. So this is minus 2 10 to negative 9 Coulomb. This is 4 10 to negative 9. And this is 3 10 to negative 9. Okay. Things become really interesting because how do we account for the energy of this system of three charges? And the truth of the matter is that what you have to do is look at pairs. Okay? You have to look at pairs because if QA interacts with QB, then the two are going to have some potential energy, right? QA creates VA, QB times VA is potential energy, or the other way around, QB creates VB and QA times VB is potential energy. The point is, you always have to look at pairs. And here you have 3-point charges, actually means you have 3 pairs. And the total energy is going to be U from the pair AB plus U from the pair BD plus U from the pair AD. And once you've done that, you've found all of your pairs. Right? Now, just to be clear, UAB could either be QAVB or QBVA. It doesn't matter. Right? You can write either one. They're going to get the same thing. What you get in both cases is K, QA, QB divided by R. And then between B and D, you're going to get K, QB, QD divided by R. And then between A and D, you're going to get K, QA, QD over 2R. All right, so let's maybe, what's the smartest way to do this? We just factor everything out. So we can say it's K over R times QA, QB plus QB, QD plus QA, QD over 2. All right, that's going to be 9, 10 to the 9, divided by R, which is 3, by the way, times, this should be QB, my bad, QA, QB. So that's QA, QB is minus 2 times 4 is minus 8, 10 to the negative 18, plus B times D is going to be 12, 10 to negative 18, and then minus 6, 10 to negative 18. All right, so this is going to be 9 over 3 is 3. If I multiply 10 to the 9 into all of this, all the 10 to negative 18s become 10 to negative 9, so I'm going to write 3 times 10 to the negative 9, and then it's minus 8 minus 6 plus 12. So it's minus 14 plus 12, and that's minus 2, and so this is going to be minus 6 times 10 to the negative 9 joules. All right. So not a hard problem, but actually a very nice problem. It allows us to review a few things from the past 2 weeks, and it kind of allows us to talk about a few important topics when it comes to electric potential and electric potential energy. So that would illustrate the first 2 points that I made, which were that you can compute V, and therefore U, with a system that maybe has only 1-point charge or multiple point charges, but you would just use superposition to do that. Okay, so here we had 2-point charges at first and then eventually 3. That takes care, if we go back just to situate ourselves, that takes care of this and of this. Then we have to go over the next 2 cases. It turns out I'm going to do this one first because I want to review Gauss's law, which is what we did last week, so it's going to be a nice review of that. And then we'll do slice and dice at the very end. Okay. So this, in part, is a review of Gauss's law. I don't want to spend too much time on Gauss's law because that was last week. But I do want to show you the relationship between Gauss's law and finding the speed with which this particle hits this metallic cylinder. So we have a very long, basically infinitely long, hollow metallic cylinder that carries a uniform charge density, sigma, on its surface. And you're looking down at it from above or from the side, whatever, and you have this particle that's going to be launched as a charge minus q and a mass m, but we'll get to that in a second. Before we find anything about minus q, let's find the electric field created by the cylinder as a function of the distance r to the cylinder's axis. In other words, the electric field everywhere. Because you have two regions, you have to do Gauss's law twice. So we're going to have our cylinder like this, and we're going to look at region 1 first. This is region 1. This is region 2. Has a length L, or is infinitely long, it doesn't really matter. L is going to cancel out. And we know that we're going to do Gauss's law twice. Okay. Now in the first case, we know how to go about Gauss's law. We've done this, we did this last week, right? So if this doesn't make sense, make sure you go review, because this is all supposed to be fair game, and we assume that this is no problem at this point, that you're comfortable with doing this. So you draw a Gaussian cylinder that lives inside region 1. And the reason that you do that is because you know that your electric field is going to be radially outward, and so you're only going to get flux through the lateral side, the lateral wall of your cylinder, not through the top of the bottom. And without redoing all the details of last week, hopefully you agree that the electric flux is going to be E1 times 2 pi RL. Okay. If not, make sure you go back to the previous live stream, which was on Gauss's law, and that you look at the derivation that we did for the cylinder of charge. Redo it, convince yourself that indeed the flux is going to be E1 times 2 pi RL here. Okay. And then to be equated to Q enclosed over epsilon naught. How much charge does my Gaussian cylinder enclose? The answer is none at all, because it's a hollow cylinder. The charge lives on the surface here of the metallic cylinder, but everywhere inside the cylinder is basically air. There is no charge, so Q enclosed is 0. By Gauss's law, these two quantities are equal to each other, and we come to the conclusion that E1 is equal to 0. There is no electric field inside the hollow cylinder. Outside, however, that's a different story, because outside we will enclose the charge sigma on the surface. Okay, so to find the electric field in region 2, we have to draw a Gaussian cylinder that lives in region 2, something like this. Right. It's going to have a radius r. It's going to have a length L. And again, go back to the work we did last week if this doesn't make sense, but the electric flux is going to be E2 times 2 pi RL. Because flux doesn't know which region it's being computed in, it only knows that it's being computed through a cylinder. Therefore, flux comes out the same in both regions. Okay. So, with that said, let's equate it to Q enclosed over epsilon naught. Now, what is Q enclosed? Okay, well, this time I have charge that lives on the surface of my metal cylinder, and all of the cylinders enclosed within my Gaussian cylinder. Therefore, I have an amount of charge that is sigma times the surface area of my metal cylinder, which is 2 pi, careful, big R times L. Don't use little r. And that's over epsilon naught. And by Gauss's law, these two quantities are equal to each other. I have E2 times 2 pi RL is equal to sigma times 2 pi big RL over epsilon naught. And therefore I find that E2 is equal to sigma r over epsilon naught little r. And because my cylinder of charge is positively charged, this is going to be radially outward. Okay, so that's a bit of a quick review of Gauss's law, but again, if you're not this comfortable with Gauss's law at this point, you need to go review Gauss's law. Gauss's law takes a bit of time to kind of grasp at first and to know which Gaussian surface to choose for which problem and how to find flux. But once you've done a few, you should be able to go through it pretty quickly. And yes, on the exam, you'll probably want to show more steps than I showed here to find the flux. But if you're doing problems, you don't want to necessarily spend all your time deriving E if that's not the point of the problem. And here it's kind of not the point. I mean, yes, it's the first question, but our goal is to get to really the second question. So I know E1 and E2, and this is going to tie into me finding delta V, and we'll see why we care about finding delta V. So let me make a copy of this figure here, and then let's come down here and answer the next question. So here is our cylinder, and we're now told that a charge minus q with mass m is launched at speed v0 toward the center of the cylinder. How fast is it moving when it hits the cylinder's surface? Okay, and let's assume that it's launched from a distance little r here. That is 3 big R. And it's going to collide with the cylinder here at r equals big R. And again, let's just remind ourselves that speed upon impact is not zero, right? Otherwise, it's not an impact. So V final is not zero. We're going to figure out what it is. To figure out what it is, I'm going to use conservation of energy, because the only force that is pulling the particle toward my cylinder is the electric force, which is a conservative force. So I'm going to draw my electric field. My electric field looks like this. This is E2. In magnitude, it is sigma big R over epsilon naught little r. And I want to find delta V. Now you might say, well, how do you know that you want to find delta V? Like, because yes, you know, if you know ahead of time that you're going to do conservation of energy, that's fine. But if you've never seen this, then perhaps you're not sure why you want to find delta V in the first place. So let's actually do this. Let's write conservation of energy, because maybe it makes more sense to you to say, well, look, if you want me to find V final, let's write conservation of energy. Okay, we can do that. We can say my initial kinetic energy here is going to be 1/2 m v0 squared, and then plus, well, I need electric potential energy. Electric potential energy is QV. So this is going to be minus Q times V initial. We'll just call V initial the electric potential at this point, and capital V final the electric potential at this point. Kinetic energy upon impact is 1/2 m little v final, that's what I'm solving for, squared. And then plus electric potential energy is going to be minus Q times capital V final. Okay, so from there, I can say that 1/2 m v final squared is equal to 1/2 m v0 squared plus Q times V final minus V0. And all I did is add QV final on both sides, and then I factored it out to get this term here. And I shouldn't call it V0, I should call it V initial. Okay, this is delta V. By the way, this is why I need to find delta V by using the minus the integral of E dot dr. Now in physics, when we present solutions, we typically, because solutions always used to be written, okay, now in video format we can do things a little differently, but we never like to start solving only to say, roadblock, hold on, I now have to go compute delta V, I'll come back to this. It would be confusing if you're reading a book. You know, you start here, you're like, oh, sorry, sidebar, and then you come back. I get it, right? So when you tend to read answer keys, it's just such a habit when you teach physics to start with everything you need to then get to the answer rather than start something, hit a roadblock, go do something else, come back, okay? So that's why this would probably be after finding delta V. But mentally, it might make a lot more sense to you to say, okay, I know, the only thing I know is I want conservation of energy. Let's write it, let's see what happens. And if I hit a roadblock, then at least I know what I have to go find now. I have to go find delta V. Oh, okay, I'll go do that. So we'll do that. We'll just bring conservation of energy down here, right, so that we can return to it in a bit. But up here we want to find delta V. Okay. Delta V is V final minus V initial. And like I said before, let's just write the formula as is. So it's minus the integral from initial to final of E, which in this case is E2, dot dr. Okay. Quick reminder, but we talked about this last week when we did Gauss's law. If I have E as a vector and dr as a vector, and we're going to have to worry about dr in a second, and I have an angle theta between the two, theta might be 0 because they point in the same direction, but if you have two vectors, there's always an angle theta between them, then E dot dr is E cosine of theta dr. Okay, so that's just the definition of the dot product. It tells you how much of E is along dr. Okay, now the question is, what is dr? I know what E2 is, I know the magnitude, I know the direction, but I don't know dr. Okay, this is important, pay attention. Dr, I say this because at some point this is going to be a problem, and you're not necessarily going to realize that it is. Dr always points in the direction of increasing r. That's the simplest way to put it. Therefore, it must always point radially outward if I have a cylinder or a sphere, because the direction of increasing r is radially outward. So you don't get to negotiate the direction of dr. Dr is imposed upon you. It is in the direction of increasing r. Okay? R increases from here to here. Dr is radially outward. Now that's helpful because I know that this is therefore going to be minus the integral from initial to final, we'll get to the bounds in a second, of, based on the definition of the dot product, E2 cosine of the angle between E2 and dr, which is 0, they both point to the right, dr. Okay, so this is then minus the integral of E2 sigma r over epsilon naught little r, cosine 0 is 1, dr. And apparently I'm integrating over little r. Okay, well, initially, where am I? I'm here. R is what? 3r. So this is from r equals 3r all the way to r is equal to big R. And that's getting a little crowded, so let's try to make that a little bit easier on the eyes. There we go. Okay, and now a little bit of calculus. Quick reminder that the integral of dr over r is ln of r plus some constant, although we don't care about the constant here because we have bounds. And so this is going to be sigma r over epsilon naught, natural log of little r. And I don't need an absolute value here because r is positive, right? It goes from 3r to big R, so I don't have to worry about the absolute value. All right, so this is going to be minus sigma r over epsilon naught, natural log of r minus natural log of 3r. So let's clean that up. this minus here out front, I can multiply it within the parentheses. I get this, then this goes away. And then I have sigma r over epsilon naught. And then ln of 3r minus ln of r is ln of 3r over r by property of ln. So then we get, this goes away, and we just get sigma r over epsilon naught, natural log of 3, which is a nice clean answer here. Okay, so now we have delta v. Now that we have delta v, we can come plug it into here. Okay, that's why, again, that's why most of the answer keys you would find would start by finding delta E. So this is going to be Q times delta V is going to be Q sigma R over epsilon naught, natural log of 3. So to get V final, I'm going to multiply by 2, divide by M. I'm going to get V final squared as V0 squared plus 2Q sigma R divided by M epsilon naught, natural log of 3. And then, of course, I'll just square root. Keep the positive root because I want speed. And that will be V final, the speed with which the particle strikes the metal tube. And just to revisit this real quick, the problem is called electrostatic spray painting because this is a technique used to spray paint planes. So planes are really big, I mean, commercial airlines, yeah? And they're in big hangars because that's usually where you put them. And, well, you need a big amount of paint, a large amount of paint to paint them. And the last thing you want is a magnificently large cloud of paint inside the entire hangar because the hangar is not just used for painting. And so what we'll do is we'll basically make sure that the droplets of paint come out with some charge and that therefore they get attracted to the plane. So the entire cloud of paint tends to kind of stick on, basically get attracted by the fuselage of the plane and just kind of moves toward it in one motion rather than spraying like this and getting plumes of paint particles everywhere. So it's an actual real technique which is quite useful, at least when it comes to painting planes. So there are applications to these things, even though they seem quite abstract. But this is a classic problem that you will probably find a version of on the exam, where you have a geometry that lends itself to Gauss's law. Oh great, I get to test you on Gauss's law if I'm your instructor. And then I get to test you on electric potential because I throw in a conservation of energy problem, and you know E, so now you can find delta V, I can test you on the formula, and then I can test you on conservation of energy. So very classic archetypal problem. You should be comfortable with these. And this addresses the point that we brought up earlier of finding delta V from E. Okay. And so the last point that we need to talk about is slice and dice, because, well, we finished with slice and dice 2 weeks ago when we talked about electric fields. So let's finish with slice and dice in this chapter when it comes to electric potential. Now, when we did slice and dice for electric fields, we did the semicircle. But since then, especially if you're in the Masterclass, you've seen the problems with the ring of charge, find the electric field, and then the disk and so forth. So we did the semicircle. Here I'm going to do the ring of charge. I could do the semicircle, but I want to change it up a little bit. And we have a thin ring of charge of radius r located in the YZ plane with its center at the origin as shown. It carries a charge per unit length lambda that is given at a point P, a distance L from the origin. And ignore the symbol Q at first. We don't need to worry about that. That is a leftover from poor cutting and pasting skills. There we go. Forget about that. We don't need that. Okay, give your answer in terms of the symbols R, lambda, and L, and of course any needed constants, and find the electric potential Vp at point P. Okay, fair enough. So let's find the electric potential at point P here. And let's say that, well, the only formula we know is kq over r, but it's only true for a point charge. So let's take a slice of this ring that is so small that we can treat it like a point charge, and let's find the electric potential that it creates at point P. So we've done this before, so let's do this. I'm going to draw a side view. Well, this is a side view, and I'm going to draw a view here on the left, on the side, where you're looking down at this ring from the right, like this. This is point P. Okay, and we know what to do. We need to take a slice that is the tiniest slice that we can imagine without ever being 0. Has an arc length of ds, and if this is d theta, ds is capital R d theta. Okay, capital R being the radius of this ring. This is my slice. It's right here. I could draw it anywhere, but it's a little bit easier if you draw it at the top. This slice is going to have a charge dq, is lambda times the tiny length ds, so that's lambda r d theta. And this slice is located at a distance little r from P, which is square root of L squared plus big R squared. And what I'm going to say is that at point P, the electric potential created by this little slice is dVp. It's K dq divided by R, because my slice is so small that I can treat it like a point charge. So I get to write that it's K dq over R. That's going to be K lambda R d theta divided by the square root of L squared plus R squared. And the price that I have to pay for having chosen a tiny slice so that I could use the formula from the point charge is integration over the entire charged object. So I have to integrate around the ring. And I can do that by saying that to integrate around the ring, I have to go from theta is equal to 0 to theta is equal to 2 pi. And now actually, that was a question that came up a couple of times this week in the Masterclass, where students got confused about what's theta. It's like, well, because it called this d theta, but it might not be clear what theta stands for. Theta, typically, if we follow math, we'll make theta equals 0 here, just like the unit circle. Theta is the angle that references where your little slice ds is, right? So it's going to be the angle here that tells you where you took that tiny slice. And if you want to get the entire ring accounted for, you have to sweep your slice around the ring. So you have to go from theta equals 0 to theta equals 2 pi. Now, it doesn't really matter where you pick theta equal to 0. You could pick theta equals 0 here if you want and go all the way around. The point is, to integrate around the ring, theta has to go from 0 to 2 pi. And since everything in here is constant, right, none of these quantities depend on theta. If you go around the ring, K obviously is constant, lambda is, R is, L is constant. L is some arbitrary distance. But once it's fixed, it's fixed. As you go around the ring, L does not change. And so all of these things are constants. It's very straightforward to integrate. We just have to integrate d theta, which integrates into theta. So we get K lambda R divided by the square root of L squared plus R squared. And then we get theta to be evaluated between 0 and 2 pi, and of course we get 2 pi out of that. So that's going to be 2 pi K lambda R divided by the square root of L squared plus R squared. And that's going to be V at point P. Okay. And now that we found that, we're asked, well, if a proton with mass mp and charge e is released from rest at point P, how far is it moving when it reaches infinity? That's such a good question. Okay, so then let's just say that this is our ring. This is a side view. Okay, and this is going to be, well, point P. Oops, hold on. Let's put point P right here. And we know what VP is equal to. And for convenience, let's just draw infinity. Okay. Now infinity is going to be L goes to infinity, because this is the distance L to the center of the ring. Okay, the question then is, what is V infinity? And you have to be very careful, because it's very tempting to say, oh, it's 0. We always take V equals 0 at infinity. It's like, no. We take V equals 0 at infinity, go back and check, every time we have point charges or spheres of charge. But if we have rings, semicircles, rods, infinite sheets, anything else than a point charge or sphere, we do not take V infinity is equal to 0. You have to figure out what it is, but it's certainly not 0. Okay, so this is a little bit of math. If we take this thing here, let's just do it down here. Let's change the color just to, okay, because this is a sidebar, yeah? This is, we're going to take the limit as L approaches infinity. Okay, as L approaches infinity, it is going to dwarf R. So L squared will be much bigger than R squared. So this is going to tend to approach 2 pi k lambda R divided by the square root of L squared, which of course is just L. So this is going to be 2 pi k lambda R over L. Okay. So to be clear, VP is whatever we found before, and V infinity is this. And if we release a proton with a mass mp and a charge e from rest, so V0 is 0, it will be repelled by the positively charged ring. It is going to travel in this direction, and it will reach infinity with a certain speed. Let's call it V infinity. And we want to find V infinity. Okay, well, the only force doing work on the proton as it moves is the electric force. It is a conservative force. Therefore, I get to write conservation of energy. Initial kinetic energy, 1/2 mv0 squared, which is of course 0, plus electric potential energy, which is charge E times electric potential Vp at that point, is equal to 1/2 of m V infinity squared, that's what I'm solving for, plus E times capital V infinity. All right, so 1/2 m V infinity squared is equal to E Vp minus V infinity, which is going to be equal to E Vp, which is all of this, minus V infinity, which is all of this. And let's make a little bit of room. And so we are going to multiply by 2, divide by m, and eventually square root. So we're going to get 2. Okay, we can factor out a whole bunch of stuff here. So we can factor out the whole numerator. It's going to be 4 pi k lambda r e divided by m. Okay, and I multiplied by 2 here, and I had a 2 here, so that's why I got 4. And then multiplied by 1 over the square root of L squared plus R squared minus 1 over L and we square root, and we keep the positive root because we want speed, and that is v infinity. Okay, so at the beginning of this live stream, I told you that electric potential is a very abstract chapter. Most students do not like it, partly because it's very abstract, but also partly because I think when it's taught, you get everything thrown at you at once, and it's very easy to be completely overwhelmed and not tell the signal apart from the noise. So what I tried to do today is just start somewhere. Let's go back to the very beginning here. I wanted to start with the definition and kind of make a parallel with mechanics, at least so we could make peace with the idea that we have this quantity V. What it represents is electric potential energy per charge at a point, but macro, our goal is to know how to find V, because if we can find V, then we can find U, which is QV. In fact, probably what we want to do is find delta V so that we can get delta U, at least when it comes to conservation of energy. But the point still stands. Our goal is to find V. And there are 4 different scenarios that we went through here to find V. And then we did an application of each one of those in the problems that followed. Now, are you an expert now at electric potential? No, most definitely not. But you've seen the very important pieces of electric potential, and hopefully you understand how these pieces are arranged and what the goal is. Now, of course, it's going to be very tempting for us to mix the previous 2 weeks with this week and create multi-concept problems, right? But just keep in mind that what you're trying to do for this chapter is get good at finding V, whether it means computing it directly or computing delta V through the knowledge of the electric field, because then you can use the tools that you already know about to find the electric field. So that's going to be it for the public part of this physics review. And again, I appreciate you watching. Thank you. If you don't watch, this thing doesn't really work. So thanks for watching live or watching the recording. And hopefully it clarified a few things about electric potential. As always, you cannot read about push-ups, you have to do them. So go sit down and do some problems about electric potential. Try to stay on top of the chapter, each chapter that's covered every week, because midterm is 2 weeks out, more or less, and it's going to build up real quick if you're not staying afloat. So don't put yourself in the miserable situation where the week before, the 2-3 days before, you have to review everything. Physics doesn't really lend itself very well to that. Although, yes, there's always an exception, but we don't reason by exception, okay? We don't say, oh, but my friend could do it. He just read his book the night before and aced the test. Yes, I had friends like that. They were much smarter than I am, than I was back then, and then I probably much smarter than I am now. But they could do that. Most of us can't. Most of us have to put in the work and stare at these problems and, try to wrestle with them to understand these concepts. Anyway, that's my mini lecture. So try to stay on top. You'll be happy you did, and you know where to reach us if you have questions or if you need more help. You can go to psychedemia.com. You can find all of these live streams packaged into a free course. I encourage you to sign up for the course. I think you'll find it helpful. And if you need more help, we have study guides that will allow you either to self-study or to join our Masterclass. Just don't wait too long. Masterclass has limited seats. So if you want to make sure that you can get as much help as you need for this course, and a guarantee that if you don't get an A, we will refund you 90% of the cost, then don't wait too long, because we do tend to sell out before, usually before midterm 2. So with that said, I will see you next week. Next week we will we'll move on to something nicer. We'll move on to capacitor, which is kind of a breather, because it'll help us review things that we've learned so far, and it will apply them to capacitors that are very straightforward components in circuits. It's a lot easier, or at least it seems a lot easier and a lot more practical than everything we've done so far. So we'll talk about that, and that's going to be our first step toward circuits, which will come after that. So we're slowly trying to move through electric fields, which we've done a big chunk of, and into a bit of the applications through DC circuits. And then after that, we move entirely into magnetic fields, which is a different story altogether. But next week, I'll see you and we'll talk about capacitors. Have a great weekend. Thanks for watching.